Okay, so let's have a look at the 2015 Higher Level Leaving Certificate paper, Maths Paper 2, and we're just going to have a look at question 8. So, first part of this question, well, the question itself generally involves basketball, and in basketball, players have to take free throws. Michael takes his first free throw in any game. The probability that he's successful is 0.7. Now, for subsequent free throws in the game, the probability that he is successful is 0.8 if he has been successful on a previous throw, and 0.6 if he's been unsuccessful on a previous throw. So you would imagine that would be roughly correct. If he was successful, he would be more confident with his next throw. If he was unsuccessful, he would be less confident with his next throw. So what we have to do in part A here is find the probability that Michael is successful with all three of his first 3 free throws in the game. So let's have a look at that. We want the probability. We want the probability that he is successful, and then in the next throw successful, and in his next throw successful. So if he is to be successful, let's see, the probability that he is successful on his first free throw, we're told, is 0.7. So that's just going to be 0.7. And here means just that we've got to multiply. Now, he was successful here, so what's the probability that he's successful on his next free throw? Then was just going to be 0.8. 0.8. When he's successful once, the probability that he's successful the next time is 0.8. Now if he was successful here, then it's going to be 0.8 the next time again. So when we multiply all that out, we get 0.0448. And that's it for part A. Let's have a look at part B. Find the probability that Michael is unsuccessful with his first 2 free throws and successful with his third. So let's just write that out. That's the probability that he's going to be unsuccessful, and then he's going to be unsuccessful again. That's unsuccessful with his first 2 free throws, and then successful, and then successful with his last throw. So on his first throw he's unsuccessful. So we know that the probability that he's going to be successful on his first throw is 0.7. We had it here, so that means being unsuccessful on his first throw is 0.3. And here, that just means multiply. Now if he was unsuccessful with his first throw, that means the probability that he's going to be successful with his next throw is 0.6. Now we want him to be unsuccessful with his second throw. So if he was, let's see, for subsequent free throws in the game, the probability that he's successful is 0.6 if he has been unsuccessful. So that means that if he has been unsuccessful, the probability that he's going to be unsuccessful again is 1 minus 0.6, which is 0.4. So being unsuccessful here after being unsuccessful in a previous throw is just 0.4. Multiply that again. Now he was unsuccessful here, now we want him to be successful, so the probability that he is successful after being unsuccessful is 0.6. So we multiply by 0.6 here. When you multiply those 3 out, you get 0.072. So that's the probability that Michael will be unsuccessful and unsuccessful and then successful. 0.072. Okay, so let's look at part C here. We need to list all the ways that Michael could be successful with his third free throw in a game, and hence then find the probability that Michael is successful with his third free throw. Okay, so what way can this happen? Well, he can be, let's see, he can be successful and successful and successful. We had that in part 1. That was just 0.072. Or he could be unsuccessful and successful and then he could be successful again, or he could be unsuccessful and unsuccessful again and then successful, or finally then he could be successful and unsuccessful and then finally successful. Okay, so we've got to work out all these probabilities. Now the final probability then is going to be, we've worked this one out in part 1 and it was just 0.448. Or here, the word or here means we're going to have to add our probabilities. So being unsuccessful, successful and successful, so what's that going to be? Well, to be unsuccessful in the first shot is going to be 0.3. Got to multiply that. If he was unsuccessful, the probability that he's going to be successful then is 0.6. We were given that in the question. If he was successful here, the probability that he's going to be successful again we were given that in the first part of the question, is just 0.8. Okay, or means we add again. We want unsuccessful, unsuccessful and successful. We did that up here in part B and we found that to be 0.072. And then finally we've got to work out the last one here. We want him to be successful in the first free shot, is just going to be 0.7. And then to be subsequently unsuccessful. Well, for him to be successful, as we see up here, if we read this line here, for all subsequent free throws in the game, the probability that he is successful is 0.8 if he was successful on a previous throw. So if he was successful on a previous throw, the probability that he's subsequently going to be unsuccessful then is just 1 minus 0.8, which is 0.2. And that's what we need here. So we need a 0.2 here. Now he was unsuccessful here, so the probability that he's going to be successful here is just going to be 0.6. We were given that at the very beginning. So okay, after this we just got to work all these out. So it's going to be 0.448 plus 0.144 plus 0.072 plus the last one is 0.084. And when you add all those up you get 0.748. So we've listed all the ways that Michael could be successful with his third free throw in the game. So successful here, here, here and here, and the subsequent two free throws as well. And we found the probability that Michael is successful with his third free throw, then it's 0.748. Okay, so let's have a look at part D then. Now in part D here, let's see, let Pn be the probability that Michael is successful with his nth free throw in the game, and hence 1 minus Pn is the probability that Michael is unsuccessful with his nth free throw. Show that Pn plus 1 is equal to 0.6 times, or 0.6 plus 0.2 times Pn. Okay, now we have Pn is equal to the probability of success on the nth throw. Probability that Michael will be successful on the nth free throw in the game. Now, so that would just mean then, if we want Pn plus 1 here, Pn plus 1 is equal to the probability of success on the n plus 1th throw. Now, Pn plus 1, what way can the throw work out for the Pn plus 1th, or for the n plus 1th throw? So it can be, he could have been unsuccessful and then successful. So in other words, this is the n plus 1th throw here. Just to say this is the nth throw. This would be the n plus 1th throw here. Now, or he could have been successful and then successful. So again, this would have been his nth throw, this would be his n plus 1th throw. So we're just looking at both possibilities here. What could have happened on the nth plus 1 throw? He could have been unsuccessful previously, or he could have been successful previously. There are only two options. He either got the previous shot or he didn't. So these are our two options. So what happens here then? So we're looking at the probability of n plus 1. What's going to happen on the n plus 1th throw here? Well, that's just going to be the probability of being unsuccessful, and we're told that here is just 1 minus Pn. That's the probability. We're told that here 1 minus Pn is the probability that Michael is unsuccessful with his nth free throw. This is our nth free throw here. And we got to multiply that by the probability of success then. So we know this from the very first part of the question. If Michael was unsuccessful, what's the probability that he's going to be successful in the subsequent throw? Well, it's just 0.6. We were given that at the very beginning. Or here means we add. Now, what's the probability of being successful on the nth free throw? Well, we were told that at the very beginning of this part of the question. Let Pn be the probability that Michael is successful with his nth free throw. So we're going to stick Pn in here. Remember, where we want to end up is here. Pn plus 1 is equal to 0.6 plus 0.2 Pn. So we need a Pn in the answer. So here's we have a Pn here and we have a Pn here. We have our Pn plus 1 over here. And means we multiply, and now we have the subsequent throw. Well, we know that if Michael was successful in the previous throw, the probability that he's going to be successful now is 0.8. So this should, if we simplify it, we should end up with this equation here, hopefully. So let's see what happens. Well, we've got 0.6 times 1, which is 0.6. We have minus 0.6 minus 0.6 times Pn. We've got plus here 0.8 times Pn is just 0.8 times Pn. Now here we just end up with, well, we have a 0.6, that's perfect, that's exactly what we needed. And here we got our Pn plus 1. Now we got a minus 0.6 Pn plus 0.8 Pn, that's just plus 0.2 times Pn, and that's exactly what we were asked to find. Okay. Let's move on to the next one then. This is quite a long question, so let's see. We have part 2 here. Now, assume that P is Michael's success rate in the long run. That is, for large values of n, we have Pn plus 1 is roughly equal to Pn, which is P. Now, using the result from D1, that's just what we've just done up here, just this part here. Using this result here, or otherwise, it's probably best to use this result here. Show that P is equal to 0.75. So let's have a look at that. We're given that P n plus 1 is approximately equal to Pn, which we're calling P here. Now we know here that Pn plus 1 then must be just equal to, we're using this result here, so Pn1, these three here are roughly equal, so we already have an expression for Pn plus 1 here. It's 0.6 plus 0.2 times Pn. Now if we use this here, this Pn here, these are all equal, remember. We have a 0.2 Pn here, bring that over to this side, or subtract 0.2 Pn from both sides, so we just end up with 0.8 times Pn is equal to 0.6. So that finally will just give us Pn here is equal to 0.6 divided by 0.8, and that's just 0.75. And that's what we were asked to find here. Show that P is equal to 0.75. So we've just divided by 0.8, divided both sides by 0.8. Okay, so that's that part of the question. Let's have a look at part E then. So part E, for all positive integers and let an equal to p minus pn, where p is 0.75 as above. So we worked out p already. Use the ratio an plus 1 divided by an to show that an is a geometric sequence. So this an here is some kind of geometric sequence, and we're told that the common ratio, well, we've got to show that the common ratio is 1/5. Okay, so look, geometric sequences are just, I mean, this is just an example here, nothing to do with the question directly, but if you have 2, let's say 6, 18, 54, and so on. This is a geometric sequence here, where our first term here is 2, and our common ratio, what's called a common ratio here, is just given by dividing one term by the previous term. So if we take 6 and divide it by 2, if we take 6 divided by 2, we should get our OR here, which in this case is 3. If you take 18 divided by 6, you should also get 3. If you take 54 divided by 18, you also get 3. So this is called OR, or a common ratio. So we're told here that an plus 1 divided by an, we've got to show that this, we're going to use this ratio rather to show that an is some kind of geometric sequence with a common ratio 1/5. Well, let's see what we have already. We know that an is p minus pn. So we can write that in here. So an plus 1 then is just going to be p minus pn plus 1, because we're told here an is p minus pn, so an plus 1 must be just p over pn plus 1. An then, we're given that in the question, so it's p minus pn. So we've got to show that this is equal to 1/5. So we're taking any term, dividing it by its previous term to find a common ratio. Okay, so let's see what we can do with this. P now we know is 0.75. Okay, we're told that here P is 0.75. We worked that out in a previous question anyway, 0.75 minus Pn plus 1. Well, Pn plus 1 Pn plus 1 we have here. Pn plus 1 is equal to 0.6 plus 0.2 times Pn. We worked that out previously. So let's write that in. So I'll just put that in brackets here. We have 0.6 plus 0.2 times Pn. Divide that by An. So we got P, which is again is just 0.75, minus Pn, which is just again just Pn here. Okay, so let's work this out. Let's just see if we can simplify this. Now let's take away the brackets. We got 0.75 minus 0.6 minus 0. Plus minus 0.2 times Pn. 0.75 minus 0.6 minus plus is minus, so that's fine. Okay. So on the bottom here we have 0.75 minus Pn. Now 0.75 minus 0.6 is just 0.15 minus 0.2 times Pn over 0.75 minus Pn. Now remember, this doesn't look much like 1/5, but the fact that there's a 5 there should maybe give you a clue that if you can factorize out maybe a 1/5 here somewhere, or a 5 here somewhere, it would be handy. But if you look at this 0.15, if we multiply it by 5, we'll get 0.75. If we take this 0.2 and multiply it by 5, we'll get 1. Remember, there's a 1 here. So what I could do, I'll just come up here. Actually, I'm kind of running out of room here, but what you can do here is write the top line down again, 0.15 minus 0.2 times Pn, and we know that if we multiply on the bottom 0.15 minus 0.2 Pn, that's actually the bottom line. 5 times 0.15 is 0.75, 5 times 0.2 is 1. So this here will give us our 1/5. We can just divide those two, divide this into this, we'll get 1 on the top, so we'll just get 1 over 5. And this is our common ratio, or in other words, if we take any an plus 1, any term, divide it by the previous term, we'll get a constant, and that constant is 1/5. So that shows that an is a geometric sequence with common ratio 1 over 5. Okay, let's look at the next one then. This is part 2. Now in this particular case we've got to find the smallest value of n for which p minus pn is less than 0.00001. Okay, now let's see, where will we go from here? We know that let's see, we know that an is equal to p minus pn. This is from E part 1, where we know that p is equal to, p here is equal to 0.75. We know that from previous questions. Now we know that this is an is a geometric, it's a geometric sequence here, so we can work out the first term here. Our first term in our geometric sequence would just be a1, where n is 1. That will give us p here, which is, we know p is, well really it's just p minus p1 if you like. Now we know here that p is 0.75, and p1 then, p1 is actually, what is p1? If you think about where this whole question started, p1 is just the probability that Michael is successful on his first throw. That's what p1 is. It's the probability that Michael is successful on his first throw. And we know that from the question, we know that that's 0.7. They told us that at the very beginning, 0.7. So in other words, our first term then is just simply 0.05. 0.05. Now, we also know that for any particular term in a geometric sequence, Tn is just going to be a times r to the power of n minus 1. So if we take our a here as being 0.05, we know that. Our or here is 1/5. We worked that out in the previous question. So our 1/5 here, I'm going to call it 0.2. 1 over 5 is just 0.2, and we've got an n minus 1 here. So this is our formula for our particular geometric sequence. We worked out what our first term is. We knew that our common ratio, if you like, is 0.2 or 1/5 from the previous question. We want this to be less than 0.00001. So this is what we've got to work out. Question is, find the smallest value of n for which p minus pn is less than 0.00001. Okay, so let's find this value of n. So first thing I'm going to do is divide across by 0.05. So that will give me 0.2 to the power of n minus 1 less than, if I divide this by 0.05, I'll get 0.0002. Okay, now this is as far as we can go for the moment without getting into logs, because we have a power here and our variable is part of the power. So what we're going to have to do is get the log. I'll use natural log here. We're going to have to get the log of both sides. 0.2 to the power of n minus 1 less than the log of 0.0002. From here, just use the law of logs. Take this power here, bring it down to the front, which we can do. So that's n minus 1 times log 0.2 less than log 0.0002. Now, next thing I'm going to do is divide across by, this is multiplied, remember, so I'm going to multiply across by log 0.2. You just got to be a little bit careful here. You got to realize that log 0.2 is actually a negative number. So being a negative number, we've got to switch this, because we're dividing by a negative number, we've got to switch this symbol around. So we just get log 0.0002 divided by log 0.2. Okay, so that will give me n minus 1 being greater than 5.292. 5.292. All I've got to do now is just add 1. That'll give me 6.292. So add 1 to both sides. Now the number of throws is a discrete numerical value, so we can't have 6.2 throws. Either throw 6 or you throw 7. We want n to be greater than 6, so that means our n in this case is equal to 7 throws. So that would be, what was the question we were actually asked? We were asked to find the smallest value of n for which p minus pn is less than 0.00001. So the smallest value of n would be n is equal to 7. So this is our answer here. Okay, so let's have a look at the last two parts of this question. We have part F1 here. So you arrive at the game at which Michael is playing. You know that he has already taken many free throws, but you do not know what pattern of success he has had. Based on this knowledge, what is your estimate of the probability that Michael will be successful with his next free throw of the game? Well, we can only really go by what we've done earlier, and that's 0.75. I think how far back do we have to go here? Let me see here. P is equal to 0.75 is above, so we proved it here, we showed it here. Assume that P is Michael's success rate in the long run. That is, for large values of n, we have Pn plus 1 is equal to Pn is equal to P. Show that P is equal to 0.75. So the probability then, we come back down again. The question is, you've arrived at the game in which Michael is playing. You know that he has already taken many free throws. You don't know what the pattern of success he has had. We're estimating the probability that Michael will be successful, so that's the best estimate we have, 0.75. Now the last part of this question here is to do with Bernoulli Trials. So why would it not be appropriate to consider Michael's subsequent free throws in the game as a sequence of Bernoulli trials? So we need really 4 conditions to satisfy the trials being Bernoulli. We need to have success or failure, and we have that. He either makes the free throws or he doesn't, so that one is fine. Set number of trials, we need a set number of trials. So we could do that. I mean, we could say he's taken 10 free throws or 15 free throws or whatever. So we could do that possibly, yeah. Now the other two is where the problem comes in. We need the probability of success. We need the probability of success to be the same for each trial, and this doesn't work. The probability of success changes. We saw that at the very beginning. of the question. They gave us different probabilities depending on whether he was successful or unsuccessful in a previous throw. And the last one is that trials need to be independent. Trials effectively are not independent. Trials are not independent in this particular case. So the probability of him being successful or not successful with a particular throw changes depending on the previous throw. So trials are not independent. This would be the answer here. Or the probability of success changes with each trial. So that's really it for this question.